Far inside Norway, a quiet valley has produced light that witnesses and instruments still struggle to explain.
Unlike a fleeting rumor, the Hessdalen phenomenon returned often enough to attract organized scientific attention.
During the early 1980s, reports increased sharply and transformed a remote community into an international mystery. Some residents described brilliant objects near houses, fields, and mountains, rather than distant points among the stars. Reports were not confined to darkness, because unusual lights were also described during daylight conditions. Individual events reportedly lasted from brief moments to extended periods, complicating any single order. Witness accounts included stationary glows, slow drifting motions, and sudden acceleration through the valley. Observed colors varied, suggesting either different processes, changing conditions, or several unrelated sources.
Several descriptions emphasized exceptional brightness, sometimes strong enough to illuminate nearby terrain or dominate the sky.
Repeated observations eventually pushed the mystery beyond folklore and into a structured field investigation. Project Hessdalen began systematic observations using instruments instead of relying solely on memory and testimony. The first major campaign recorded dozens of light events, confirming that investigators had something repeatable to study. Photographs created permanent records, although image quality and distance still limited confident identification. Without reliable distance, brightness and speed estimates can change dramatically, even when the image looks impressive. Triangulation can constrain location, but useful results require synchronized observations from separated positions. An automatic station later monitored the valley continuously, reducing dependence on witnesses being present at the right moment. Continuous monitoring offered a crucial advantage because instruments could capture events that appeared without warning.
Automated images documented luminous events, yet a photograph alone could not reveal the underlying physical mechanism.
Radar observations were especially intriguing because some detections suggested more than a simple optical illusion. Different instruments did not always agree, indicating that reported events may belong to more than one category. Before proposing exotic physics, investigators must remove aircraft, astronomy, reflections, and human lighting from the sample. Some sightings can be matched with aircraft, especially when blinking patterns and predictable trajectories are visible. A bright planet near the horizon can appear to move when clouds, terrain, and the observer shift. Road traffic and atmospheric refraction may explain certain lights seen from specific viewing angles. Optical mirages can relocate ordinary sources, although they do not automatically explain every recorded event. Digital sensors may exaggerate brightness or create ghosts, making careful calibration essential for unusual light research. An overexposed image can hide shape, color, and structure instead of providing additional detail. A mysterious photograph becomes scientifically useful only when location, timing, calibration, and environmental conditions are known. Changing cloud cover can produce dramatic behavior from ordinary sources that remain stationary behind it.
After obvious explanations are removed, a residue of better documented observations still demands closer examination.
Spectroscopy matters because emitted wavelengths can reveal which atoms or processes produce the observed glow. Preliminary spectra suggested luminous gas, but limited data prevented a definitive chemical fingerprint. Certain observations did not resemble a straightforward incandescent lamp, increasing interest in natural atmospheric mechanisms.
Hessdalen's geology became central because unusual minerals, faults, and water could support electrical or chemical.
One hypothesis proposes that stressed rock generates electrical charge capable of influencing the atmosphere above. Piezoelectric effects are physically real, yet scaling them into persistent airborne lights remains difficult. Another model treats opposing valley slopes and flowing water as parts of a natural electrical cell.
Conductive water could link geological regions,
although measured energy must still account for the light's intensity. Any successful geological theory must explain where enough power originates and how it reaches the air. Radioactive radon has been proposed as an ionization source that could help charge airborne particles. A dusty plasma model could produce luminous structures under special electrical and atmospheric conditions. Researchers must explain not only light emission, but also compact shapes that sometimes appear sharply bounded. Reported motion can challenge passive cloud models, when luminous objects seem independent of local wind. Humidity, aerosols, and temperature gradients may determine whether electrical processes become visible or remain hidden.
Ionized air naturally emits photons, but the triggering energy and confinement mechanism remain uncertain. Ball lightning offers useful parallels, although many Hessdalen events occur without obvious thunderstorms nearby.
Combustion models suggest gases or airborne particles might react, producing light without conventional flames.
Such explanations still require a reproducible fuel source, ignition process, and duration matching observations.
Laboratory analogs can demonstrate plausibility without proving that identical conditions occur outdoors. A theory becomes convincing only when predictions repeatedly match independent measurements in the actual valley. Natural environments introduce noise and variables that controlled experiments can isolate, but field studies cannot remove. Researchers must distinguish a genuine physical signal from equipment noise, interference, and statistical coincidence. Radar adds information, yet clutter and ambiguous reflections can imitate targets unless measurements are carefully cross-checked. Simultaneous detections across independent instruments carry more weight than isolated readings from a single device. Even small clock errors can create false correlations between measurements recorded by separate systems. Magnetic readings have been examined, but associations with visible lights remain inconsistent and difficult to reproduce. Local equipment can disturb sensitive magnetic sensors, so instrument placement and calibration are critical. Radio measurements must separate local technology from signals that could accompany an atmospheric phenomenon. Occasional coincidences are interesting, but rare events make statistical confidence extremely difficult to establish.
Long, quiet periods force teams to spend extensive time collecting very small samples of useful data.
Modern skies contain numerous moving lights, increasing the burden of identification for every new observation. Satellite reflections can appear suddenly and move steadily, making orbital checks an essential screening step. Meteors explain rapid flashes, but generally fail to match reports of prolonged stationary illumination. Atmospheric turbulence can make stars change color and jump, especially near a jagged horizon. In darkness, the autokinetic effect can create perceived motion even when a distant light remains stationary. Human memory is reconstructive, so immediate written records are more reliable than stories recalled years later. Testimony guides investigators toward times and locations, even though instruments are needed for physical conclusions. Terrain restricts viewing angles and can repeatedly place unrelated lights within the same part of the sky. Hessdalen may reveal unusual lights partly because residents and instruments watch a clear, dark corridor so closely. More observations do not always mean more phenomena. They may simply reflect greater attention and better coverage. A complete explanation must show why Hessdalen's specific landscape favors events that appear uncommon elsewhere. The phenomenon might emerge from several interacting conditions, rather than one dramatic hidden cause. Complex systems can remain quiet for months before crossing a threshold that produces visible behavior. Strong hypotheses should forecast measurable features rather than merely explain an event after it has happened. Prospective testing would provide stronger evidence than selecting favorable measurements after a sighting. Independent teams must reproduce findings before an attractive model can become an accepted explanation. Agreement across independent instruments and analysts would reduce the chance of unnoticed bias or equipment error. Accessible data allows outside researchers to test interpretations and identify mistakes that insiders may overlook. Calibrated imagery can estimate direction and brightness more reliably than dramatic photographs without reference points.
Determining range is crucial because every estimate of size, velocity, and power depends upon it.
A wider synchronized network could triangulate events while measuring their optical, electrical, and atmospheric environment. Recording what happens before illumination may expose the trigger that ordinary photographs always miss. Complete trajectories can distinguish drifting plasma, distant vehicles, reflections, and genuinely unusual motion. How a light disappears may reveal whether energy stops abruptly or stored material cools gradually. Higher spectral resolution could separate thermal radiation, gas emission, and reflected artificial light. Automated tracking would keep rare events centered long enough for detailed measurement instead of losing them. Infrared data could test whether the phenomenon carries substantial heat or primarily emits visible wavelengths. Atmospheric sampling might reveal unusual particles or chemistry, provided collection occurs near the right place and time. Detailed ground surveys can test whether luminous events cluster above conductive structures, fractures, or mineral boundaries.
The strongest future model would connect measured subsurface processes directly to observed light production.
Decades of work have produced plausible ideas, but no explanation accounts convincingly for every strong case. A mixed origin solution may be more realistic than forcing all observations into one mechanism. One popular name can conceal several unrelated processes that happen to look similar from a distance.
Careful classification should precede theory, because different categories may require entirely different physical explanations.
Events meeting every quality criterion are uncommon, leaving science with a small core sample. Lack of explanation is not positive evidence for extraterrestrial technology or any other extraordinary conclusion. Responsible uncertainty preserves the distinction between what instruments recorded and what researchers merely suspect. Good skepticism challenges sensational claims while remaining open to data that ordinary explanations cannot yet fit. An unresolved result can still improve instruments, methods, and understanding of rare atmospheric processes. Progress arrives through patient measurement, not through one spectacular photograph or a confident television theory. Monitoring continues, because the next useful event may appear only after weeks of silence. Quiet periods define ordinary variation, helping investigators recognize when something genuinely unusual occurs. Systematic comparison prevents researchers from treating each mysterious-looking light as a completely new phenomenon. A reliable catalog could reveal recurring classes hidden inside decades of inconsistent descriptions. Enough standardized records might expose environmental patterns invisible within isolated sightings. Apparent concentrations can disappear when researchers account for where people and instruments actually looked. Modern geophysical surveys test whether underground electrical structures contribute to the phenomenon's preferred locations. Even a strong spatial relationship would require experiments showing how geology produces visible light. Pre-registered predictions would reduce hindsight and make competing hypotheses easier to compare fairly. Failed predictions are valuable because they eliminate attractive ideas and narrow the search toward better ones. What began as a wave of strange sightings has become a long experiment in measuring rare events. Hessdalen now matters less as folklore and more as a laboratory for unexplained luminous phenomena. Few locations combine recurring reports, accessible terrain, and decades of dedicated observations so effectively. Whenever another event appears, it offers a new chance to separate ordinary sources from deeper physics. The decisive breakthrough will likely require several independent measurements, capturing the same event simultaneously.
A future explanation could be entirely natural and still reveal unfamiliar behavior in Earth's atmosphere.
Alternatively, the valley may expose a poorly understood interaction among geology, electricity, particles, and weather. The reliable conclusion is modest. Real observations exist, several causes contribute, and After decades of watching, Hessdalen still questions faster than science can deliver final answers. The mystery endures not because nothing was measured, but because the measurements have not yet formed one explanation. For more than 2,000 years, people have searched for a city that may have existed only inside one man's story. Every surviving description of Atlantis begins with two dialogues written by the Greek philosopher Plato. Plato said the story reached Greece through Solon, who supposedly heard it from Egyptian priests. But no Egyptian document confirming Atlantis has ever been found, leaving the chain dependent on Plato's own account. Plato placed Atlantis 9,000 years before Solon, far earlier than any known complex city described in his story. His Atlantis was built in rings, circular canals, bridges, harbors, walls, and a monumental center. It was described as wealthy, technologically impressive, and powerful enough to dominate much of the known world. Plato placed Atlantis beyond the Pillars of Heracles, usually identified with the Strait of Gibraltar. That single phrase moved the search from the Mediterranean into the Atlantic, and eventually across the entire world. The investigation begins with a basic question. Was Plato preserving history, reshaping memory, or creating fiction? Before testing locations, the clues must be separated from the mythology built around them later. Plato's dimensions describe an enormous capital and an island larger than many proposed archaeological candidates. The island supposedly held abundant crops, forests, metals, elephants, and a complex network of artificial waterways. Those details imply a large, warm, fertile territory, not merely a small volcanic island. Plato paired the circular capital with a huge engineered plain divided by canals and military districts. Atlantis then attacked the peoples inside the Mediterranean, until an idealized ancient Athens resisted it. This conflict is central to Plato's moral structure: imperial excess against disciplined civic virtue. After moral decline and military defeat, earthquakes and floods destroy Atlantis in a single terrible day and night. Plato even said the vanished island left an impassable shoal of mud that blocked navigation. A real candidate must fit many clues at once, not simply resemble one attractive detail. Plato often used invented stories and idealized societies to explore politics, morality, and human failure. Atlantis fits that pattern. A powerful society becomes corrupt, attacks others, and is destroyed by its own excess. Its story functions perfectly, even if no island matching every detail ever existed. But fiction can still borrow from reality, especially in a region shaped by earthquakes, eruptions, and sudden coastal destruction. That possibility leads to the most famous historical candidate, Thera, now called Santorini. Santorini's circular geography, volcanic destruction, and connection to the Minoans make it visually compelling. Yet a volcanic caldera is not the same thing as a city engineered in concentric canals. The Minoan world was wealthy, maritime, artistic, and deeply connected across the eastern Mediterranean. At Akrotiri, volcanic ash preserved a sophisticated Bronze Age town with architecture, trade, and remarkable art. The site offers something Atlantis hunters crave, an advanced settlement abruptly buried by a natural catastrophe. Around the 2nd millennium BCE, Thera produced one of the most powerful eruptions of the ancient Mediterranean. Ash reached far beyond the island, disrupting landscapes, travel, agriculture, and regional life. Caldera collapse and displaced water may also have generated destructive tsunamis across parts of the Aegean. Coastal infrastructure and fleets could have suffered heavily, weakening trade and communication. But the Minoan civilization did not disappear in a single day. It continued for generations after Thera. Plato's stated date is thousands of years earlier than the Bronze Age world of Thera and the Minoans. The chronology is a major problem for identifying Santorini directly with Plato's Atlantis. Santorini is also far smaller than the territory Plato described, and it lies inside the Mediterranean rather than beyond Gibraltar. The theory works best only if Plato altered the date, location, scale, and political story. Thera may have contributed memories of catastrophe without being the literal Atlantis of Plato's text. If Plato's location is taken literally, the search must move beyond Gibraltar into the Atlantic. One group of theories places Atlantis near the Gulf of Cadiz, where earthquakes, tsunamis, and coastal change are real. Remote images have repeatedly produced shapes that look promising, until archaeology demands stronger evidence. Without inscriptions, datable architecture, and a matching settlement, geometry alone cannot identify Atlantis. Another popular theory points to the Rishat structure in Mauritania because its rings resemble Plato's city. The resemblance is striking, but the structure is a natural eroded dome far inland and vastly larger than a city. Its circles formed through geology and erosion, not through walls and waterways built by an ancient civilization.
The Azores have also attracted theories because they rise above the mid-Atlantic ridge.
But volcanic islands on oceanic crust are not fragments of a vanished continent, comparable to Plato's enormous island. Modern plate tectonics makes a suddenly sunken Atlantic continent geologically implausible. Atlantis is unproven, but real cities and landscapes have disappeared beneath water. In 373 BCE, the Greek city of Helike was destroyed by earthquake and flooding. Helike demonstrates how a real city can vanish quickly through earthquake, subsidence, and water. Pavlopetri preserves an actual prehistoric town beneath the sea, complete with streets and structures. Many ancient coastal landscapes drowned gradually as global sea level rose after the last ice age. These drowned worlds are real, but they usually vanished over centuries or millennia, not a single night. A credible Atlantis discovery would need a complete archaeological context, not a mysterious shape or isolated artifact. Different disasters leave different evidence: erosion, sediment layers, broken structures, subsidence, and datable occupation. The ocean floor is full of patterns that can imitate walls, roads, pyramids, and harbor shapes. Underwater archaeology must distinguish intentional construction from geology, erosion, and modern material. Geology does not prove whether Plato invented Atlantis, but it rules out many literal interpretations. There is no geological space for a recently vanished continent-sized island between Europe, Africa, and the Americas. Modern bathymetry maps the Atlantic floor in enough detail to reject an enormous sunken landmass. Islands can sink gradually as crust cools, erodes, and subsides, but not as intact empires in a single night. Rapid submergence is possible locally, especially during earthquakes, landslides, or volcanic collapse. A volcanic island can lose enormous volume suddenly, creating memories of land destroyed by the sea. Plato may have combined several familiar kinds of catastrophe into one perfected story. That would explain why parts of Atlantis feel historically plausible, while the complete package remains impossible to locate. The story's political and moral precision may matter more than its geographic precision. If Atlantis was designed as philosophy, searching only the seafloor may miss the point of the story. Atlantis did not remain inside Plato's dialogues. Later centuries repeatedly rebuilt it for new purposes. As ancient texts returned to European readers, Atlantis became a geographic puzzle rather than only a philosophical tale. In the 19th century, writers transformed Atlantis into a lost mother civilization behind Egypt, Mesoamerica, and other cultures. Archaeology does not support the idea that one vanished Atlantic empire created the world's ancient civilizations. Real ancient societies have deep local histories that do not require Atlantis to explain them. Modern esoteric traditions added crystals, advanced energy, psychic powers, and technologies Plato never mentioned. Film, television, novels, and games turned Atlantis into a flexible symbol of lost knowledge. Because the original location is uncertain, Atlantis can be placed almost anywhere imagination needs it. Removing later inventions makes the central problem clearer. Plato is still the only ancient source for the complete story. That does not automatically make Atlantis false, but it sets a very high standard for claiming it has been found. Every proposed Atlantis can now be tested against the same evidence rather than judged by visual resemblance. Santorini fits volcanic disaster and Bronze Age wealth, but fails major chronological and geographic clues. The Gulf of Cadiz fits the western location better, yet no accepted archaeological Atlantis has emerged. The Rishat structure looks extraordinary from above, but its geology and archaeology do not match Plato's city. The Azores satisfy the Atlantic imagination more than the geological and archaeological evidence. Most candidates become convincing only when one clue is emphasized and several others are rewritten or ignored. A strong historical identification should make the evidence converge, not require continuous exceptions. No inscription, city plan, datable archive, or archaeological layer has identified a place as Plato's Atlantis. The absence of proof is not proof that every inspiration was invented, but it limits what can honestly be claimed. The most defensible answer may be that Atlantis is philosophy built from recognizable historical fears, and disasters. The problem is not a shortage of possible locations. It is the ease with which almost any circular or submerged feature can be made to resemble the legend. Near the Bahamas, the Bimini Road has often been promoted as an Atlantean structure, despite strong geological explanations for its formation. Regular shapes can emerge naturally when rock fractures along joints and is later exposed by erosion. Yonaguni's terraces look architectural, but geologists can explain much of the structure through layered sandstone, fractures, and erosion. Archaeologists do not identify cities from shape alone. They look for construction methods, occupation layers, tools, pottery, and organized space. Remote sensing is excellent for finding targets, but shadows, resolution limits, and processing can create persuasive illusions. A genuine discovery must preserve relationships between structures, artifacts, sediments, and time. Dating matters because a spectacular ruin from the wrong century cannot be Plato's Atlantis. The location must also fit the travel routes, polydometry, political geography, and scale of the original account. An empire powerful enough to challenge the Mediterranean should leave evidence beyond a single later philosophical narrative. When a theory survives only by changing every failed clue, it stops being a testable identification. A useful theory must risk being wrong. Otherwise, every absence becomes hidden proof, and every contradiction becomes part of the mystery. Atlantis survives because it feels both impossible and familiar, a perfect city assembled from real human anxieties. It promises lost knowledge, warns against power, and turns natural disaster into moral judgment. The city vanishes beneath the sea and reappears inside the text that created it. For Plato, Atlantis may have been less a destination than an argument about what societies become. That warning remains understandable because powerful societies still imagine themselves permanent. The search will continue because every unexplored coastline and strange formation offers another possibility. But the more evidence-y this is compared, the harder it becomes to defend one literal lost super-civilization. What remains is still extraordinary, a fictional or reshaped city that became more famous than many real ancient places. Atlantis may never be found, because the complete Atlantis may never have existed outside Plato's narrative. Yet the legend preserves real truths about earthquakes, floods, collapsing powers, and the human fear of losing everything. The most important discovery may not be where Atlantis was, but why people keep needing it to be real. Atlantis remains suspended between memory, philosophy, disaster, and desire. That uncertainty is not a weakness of the legend. It is the reason the legend never stops moving. Atlantis may be history, borrowed memory, philosophical fiction, or some mixture we can no longer separate. What we can say with confidence is simpler. The story is real, the search is real, and the city remains unproven. Beyond the pillars, the map still offers room for imagination. But evidence must decide what becomes history. For now, Atlantis belongs where it began, inside Plato's dialogues, and inside the questions they still create.
The lost city remains lost, not beneath a confirmed sea, but somewhere between ancient catastrophe and the power of a perfect story.
For 2,000 years, an impossible machine lay broken beneath the sea, mistaken for little more than corroded debris. Nothing about the object looked like a computer. It looked like a stone fused with green-black bronze. The object came from a Roman-era shipwreck, loaded with art, luxury goods, and scientific knowledge from the Greek world. Greek sponge divers found the wreck by accident around 1900, beginning the first major underwater archaeological recovery. The divers raised statues, pottery, coins, and one fragile mass whose real importance, documentary, remained hidden. Among spectacular sculptures, the small bronze fragments attracted little attention at first. Then a crack revealed something no natural rock should contain: a precisely toothed wheel. The lump was not decoration. It was the remains of an intricate mechanical calculator. A single turn could transmit motion through a network of gears and transform time into positions on the sky. This machine could model astronomical cycles, track calendars, and predict eclipses more than 2,000 years ago. Only about 1/3 of the original mechanism survives, divided today into 82 fragments. The largest fragment preserves the machine's structural core and the most recognizable surviving gear. Understanding it took generations, because corrosion hid the mechanism's internal structure and most of its inscriptions. Early scholars first called it an astrolabe, a navigation instrument, or a mechanical calendar. Later researchers realized the fragments contained a clock-like gear system far more complex than expected. X-rays made the invisible machinery visible, allowing researchers to count teeth and trace gear trains. Modern computed tomography later uncovered thousands of characters that had remained unread for nearly 2 millennia. The inscriptions were not decoration. They described displays, cycles, and instructions for operating the machine.
The original device was housed in a wooden case, with dials and instructions on both sides.
Its power source was simple: a human hand turning a crank. The computation happened mechanically. The gears were bronze, thin, and hand-cut, with triangular teeth rather than modern clock profiles. Every wheel required careful layout, cutting, filing, and fitting, with the tools available in the Hellenistic world. The challenge was not merely making gears. It was fitting many calculations into a compact, layered machine. The surviving fragments suggest a device only about the size of a small box, yet packed with linked cycles. Nested shafts could carry different motions to several pointers sharing the same central display. The front display combined a calendar ring with the zodiac, turning dates into celestial positions. Set the date. Turn the crank, and the entire mechanical sky advances together. The front dial displayed the sun and moon against the calendar and zodiac. A small rotating sphere could show the moon's changing phase as its position shifted relative to the sun. The phase display was a mechanical calculation of the changing angle between the sun and moon. But the moon does not move across the sky at one perfectly constant speed. The mechanism modeled that irregular motion with an ingenious pin and slot system. As the pin moved through the slot, the moon pointer alternately accelerated and decelerated. This translated an ancient theory of the moon's unequal motion into physical bronze. The mechanism also accounted for the slow rotation of the moon's orbital anomaly over several years. On the back, a 5-turn spiral tracked the 19-year metonic cycle. After 19 solar years, the phases of the moon returned to nearly the same calendar dates. The gears converted that long relationship into a repeatable mechanical calendar. Additional cycles refined the calendar, correcting the small mismatch that accumulates over decades. The back of the mechanism carried 2 major spirals, one for the calendar and one for eclipses. The lower spiral tracked the Saros, a cycle that brings similar eclipses back after 223 lunar months. When the pointer reached an inscribed cell, the machine indicated that an eclipse was expected. The inscriptions distinguished solar from lunar eclipses and encoded details about their expected appearance. Tiny notes could describe timing, direction, and other characteristics associated with an eclipse event. A Saros repeats eclipse geometry, but Earth's rotation shifts where the event is visible. A longer exoligmos cycle helped correct the time of day shift across 3 Saros periods. One hand-powered input coordinated calendars, lunar motion, and eclipse cycles across the entire machine. The mechanism compressed decades of astronomical knowledge into a device that could be explored in minutes. Its eclipse mathematics drew on long cycles known from Babylonian astronomical observation. Greek mathematicians transformed those cycles into geometry, ratios, and finally moving machinery. The machine also tracked the 4-year cycle of major Greek athletic festivals. Its inscriptions name festivals including Olympia, Isthmia, Nemea, and Pythia. For its owner, astronomy, calendars, civic life, and sacred festivals belong to one connected system. The covers carried a technical description of the displays, almost like instructions engraved onto the machine itself. The surviving text describes a front display of the ancient Greek cosmos, including the known planets. But the front mechanism is the most damaged part, so its complete design remains debated. Different reconstructions can fit parts of the evidence, especially where gears and pointers are missing. A successful model must match the physical fragments, the tooth counts, the available space, and the inscriptions. Modern teams have proposed compact planetary gearing that recreates the ancient order of the heavens. If the reconstruction is broadly correct, the front was a moving mechanical cosmos. The mechanism reflected the geocentric astronomy of its time, a moving sky organized around Earth. Planetary motion includes apparent reversals, making a complete mechanical display extraordinarily difficult. Ancient Greek models explained these reversals with combinations of circles moving on circles. A gear system could translate those geometrical circles into the motion of a pointer. X-ray readings preserve long cycle numbers, linked by one reconstruction to Venus and Saturn. The known planets were Mercury, Venus, Mars, Jupiter, and Saturn, each with a different repeating pattern. Any planetary system had to fit many motions into extremely limited mechanical space. That is why reconstructions are tested not only mathematically, but mechanically. The parts must actually fit and turn. The surviving evidence supports remarkable sophistication, but some details of the original front remain unresolved. The mechanism is both understood and mysterious. Its core functions are clear, while its complete form is still being rebuilt. The mechanism emerged from a Mediterranean world where astronomy, mathematics, engineering, and trade crossed borders. Who designed it remains uncertain, and several centers or intellectual traditions have been proposed. Its maker combined theoretical astronomy with the practical knowledge of a highly skilled bronze workshop. Every gear ratio encoded a numerical relationship between cycles in the sky. The machine appears to combine Babylonian cycles, Greek geometry, and an Egyptian-style calendar ring. It was not an isolated miracle. It was a synthesis of knowledge accumulated across cultures and centuries. The device may have served teaching, demonstration, calculation, prestige, or several purposes at once. No surviving text tells us exactly who owned it or how often it was used. Its final journey placed it among valuable cargo moving through the late Hellenistic Mediterranean. The ship was probably carrying Greek goods toward wealthy Roman markets when disaster struck. Justing than sense. Statues, pottery, coins, timber, and the mechanism entered a cold, corrosive underwater archive. The wooden housing vanished, bronze plates fractured, and corrosion slowly welded gears into mineral masses.
Most of the original machine disappeared, leaving researchers to reconstruct a complex whole from scattered remnants.
Every modern reconstruction is therefore a negotiation between hard evidence and carefully limited inference. The goal is not to build the most spectacular machine, but the simplest one that explains the evidence. When a model aligns with the fragments, inscriptions, and mechanics, it becomes a testable historical hypothesis. Working replicas let researchers test whether proposed gear trains can move without jamming or contradiction. A successful reconstruction must reproduce the cycles described by the ancient machine.
Today, computer models and physical replicas work together to explore a computer built without electronics.
Nothing else of comparable surviving mechanical complexity appears for many centuries after the Antikythera mechanism. But the gap does not mean ancient engineering vanished completely. Most machines were recycled, decayed, or never preserved. Bronze was valuable, wood rotted, and complex instruments were unlikely to survive by chance. The mechanism survived precisely because a shipwreck removed it from the normal cycle of reuse. It may be the lone survivor of a broader tradition of sophisticated Greek mechanical astronomy. That possibility changes the question from "how was this possible?" to "how much has been lost?" New imaging can still recover details from fragments already studied for more than a century. Each newly read character or tooth count can strengthen one reconstruction and weaken another. The history of the mechanism is also a history of changing scientific interpretation. The machine keeps teaching because its fragments force historians, astronomers, engineers, and classicists to work together. Calling it a computer does not mean it resembled a laptop. It means the device mechanically processed inputs into outputs. A chosen date became a network of calculated astronomical positions and cycle indicators. It belongs to the long history of analog computation, machines that represent quantities through physical motion. The mechanism pushes the history of complex computation much deeper into antiquity. Unlike a static chart, the machine let its user explore changing celestial patterns by turning a handle. It was a manipulable model, an ancient interface for asking, "What happens when?" That makes education a plausible purpose. The machine turned difficult celestial cycles into visible motion. It may also have been a prestige object, demonstrating wealth, learning, and technical mastery. Prediction and calendar planning may have mattered, but the device was probably more than a single-purpose tool. Without its owner, workshop, or complete front display, some questions may never receive a final answer. Yet the surviving machine already reveals an astonishing idea. The sky could be calculated with gears. Inside a portable box, ancient engineers compressed generations of astronomy into bronze motion. Fragments, scans, inscriptions, mathematics, and replicas now work together to reconstruct the lost machine. Turn the crank, and a date becomes a moon phase, a celestial position, and an eclipse prediction. Its complexity was not magic. It was the result of observation, mathematics, craftsmanship, and connected cultures. From 82 fragments, researchers recovered a machine that changed what we thought ancient technology could do. It predicted the sky not by prophecy, but by encoding celestial cycles into ratios of bronze teeth. A small island gave its name to a machine that expanded the known boundaries of the ancient world. The object pulled from the sea was not an impossible computer. It was evidence of a lost mechanical tradition. And inside that corroded fragment, the ancient sky is still waiting to be read. Every compass on Earth depends on an invisible planetary shield generated far beneath our feet. Now imagine north and south slowly trading places across the entire planet. Despite dramatic headlines, a magnetic reversal would not happen during a single frightening night.
Ancient rocks preserve the direction of vanished magnetic fields, like pages in a planetary archive.
A compass does not seek geographic north directly. It aligns with Earth's surrounding magnetic field. That field begins thousands of kilometers below the surface, inside the planet's moving liquid core. Flowing conductive metal, planetary rotation, and heat together operate a vast natural dynamo. Earth's rotation helps chaotic molten motion into structures capable of sustaining magnetism. Heat escaping from the deep interior continually drives convection through the liquid outer core. From that hidden engine, magnetic influence extends tens of thousands of kilometers into space. The magnetosphere deflects much of the solar wind, yet it never blocks every particle.
Auroras appear when guided particles collide with atmospheric gases and release visible light.
Earth's magnetic field has always strengthened, weakened, shifted, and reorganized through geological time.
Scientists reconstruct earlier magnetic behavior by combining evidence from lava, sediments, and fired artifacts. Ocean floor magnetic stripes provide one of the clearest records of repeated polarity reversals. As lava cools, magnetic minerals align and permanently record the field present at that moment. Those alternating bands form a global barcode that tracks long sequences of magnetic change. Reversals are recurring features of Earth's history, although their timing follows no simple schedule. There is no reliable countdown predicting when the next full reversal will begin. Sometimes the field wanders dramatically and recovers without completing a lasting polarity exchange. One famous excursion occurred roughly 41,000 years ago and left widespread geological evidence.
Tiny magnetic particles in sediments can preserve field direction as layers accumulate over time.
Certain iron-rich minerals behave like microscopic compasses while rocks cool or sediments settle. Modern observations show magnetic poles moving because the underlying core flow continually evolves. Small changes in deep fluid motion can alter the field measured at Earth's surface. Most of the time, a large north-south dipole dominates many smaller magnetic features. During a reversal, the global pattern may become weaker, patchier, and more complicated. Real reversals likely involve tangled intermediate fields rather than one clean directional switch. Available evidence suggests full transitions unfold across centuries or millennia, not seconds. After stabilization, a reversed field would remain a functioning planetary magnetic system. Today's civilization uses magnetic conditions for navigation, communication, satellites, and electrical grid planning. A weaker field could expose some satellites to harsher radiation and operational disruptions. Radiation belts respond to magnetic geometry, influencing spacecraft exposure and electronic risk.
Airlines already monitor space weather because polar routes can face increased radiation and communication problems.
High-frequency radio links near the poles can weaken during severe space weather disturbances. Satellite navigation depends on precise timing that disturbed upper atmosphere conditions can degrade. Long electrical networks can collect unwanted currents when magnetic conditions change rapidly. Those induced currents may overheat transformers, distort voltage, and complicate grid control. A pole reversal and a solar storm are different processes, despite frequent online confusion. Electrical hazards depend heavily on how quickly magnetic fields change, not only their absolute strength. A weakened global field could alter how strongly some space weather effects reach technological systems. Greater exposure would not guarantee global collapse, because infrastructure design and preparation